Alright, today we're going to be looking at truss calculations. This is the truss we'll be working with. There are two downward forces on it, one being 500, the other being 800. It's supported by a pin support on point A and a roller support on point D. So, we're going to be solving for our static determinacy, solving then for our moments, balancing our X forces, balancing our Y forces. We'll then draw our free body diagrams and begin to solve some of our free body diagrams. So, to determine static determinacy, we go with the equation of 2J equals M plus R, J being the number of joints, M being the members, and R being the reactionary forces. If I look at my truss, I have 1, 2, 3, 4, 5, 6, 7 forces, and that is because this actually gets split into two different members there. If I can't count that as a single one because that joint is actually making the break. I'm going to count my joints now. I've got 1, 2, 3, 4, 5 of those. Alright, and then my reactionary forces. Whenever we have a pin support, it's not moving, and since this is a two-dimensional drawing, it's going to be locking it in the X and the Y direction. And this roller support is sort of like the wall pushing back on my truss, so that is just going to be in the X direction. So I have 3 reactionary forces. That gives me 2 times 5 is 10, equaling 7 plus 3. It's really nice that 10 equals 10 because that allows me to know that I can do math on this problem and I can continue on. If this didn't work out, I would actually need to pretty much restart my equation or fix my truss. So, next thing is, this is the pin that is not moving, so everything's going to be rotating around that. So my 500 and my 800 are both clockwise motions, whereas this reactionary force is counterclockwise. So my 2 clockwise are negative, and this one is positive. So the way we calculate our moments is the sum of the moments equals moment on B plus moment on C plus reactionary force D's moment equals 0. And a moment is calculated as a force times its distance. So what I have is I have my 5 feet times 500, negative 500, sorry. And then I have my 8 feet times my negative 800, plus my reactionary force times my 4 feet. So if I simplify that down, I get 225, negative 2,500, plus negative 6,400, plus reactionary force D times 4. I'm going to subtract these two values from that side, giving me this, and then divide by 4, giving me 2,225 for my reactionary force. I'm going to go ahead and plug that in. Next thing I've got to do is I've got to balance my X forces. So I'm going to sort of circle my X forces. I've got 2 of those. And I know if this one's going this way, I can't have this whole thing moving, so this is of course going to have to be going the opposite direction. So I've got 2,225 going in that direction. Next step is to balance my Y forces. I again have 3 of those. So if these 2 are going downward, I know that I'm going to have a upward force that counteracts that. So that is my 1,300. So I can plug that in. Alright. Now this is where it starts to get complicated because I'm going to start drawing my free body diagrams and working with it. So I'm just going to put in an arrow to represent where all the beams are at. Alright, and then I'm going to erase my truss from behind it. That allows me to sort of look at these as just free body diagrams. Now, individually, so I really have 5 problems here. And I'm going to look at the easiest one to solve. So pretty much it's the one with the least amount of math involved, right? So I'm looking at C, just because I've got a force going downward. I've only got one other vertical force, right? And so I can solve for that very easily. So I'm going to solve it. So what I have now is I have my 800 pounds of force going down, and the 2 blue arrows just represent that there is a member there. So I've got to think about what force is going into it. So I know that this is going to be pushing back at it because that's going to give me a resultant force. So in other words, for this diagonal force, I know I'm going to be pushing up a little bit, and that little bit right there has to be 800 to counter-react it. If not, this joint's going to be moving, and that's going to be a problem because we're going to have a truss moving. So what I can do is I can find my angle right here, and I can also write down 800, and so that gives me a triangle. So I know that this beam's coming in at a 53.13 degree angle, and this force is going to be 800, so that allows me to solve for that. So I'm going to use my sine because this is my opposite. So I'm going to take sine 53.13 equaling 800 divided by my hypotenuse. So if I do that, I get 800 divided by sine 53.13, and that's going to allow me to get 1,000 for my hypotenuse there. While I'm here, I'm going to solve for my bottom right there, because that's going to be another valued thing, because it's the amount of force that I'm pushing in at the sideways on that. And I'm going to do that by just calculating my cosine. So my adjacent, which would be this side, divided by my hypotenuse is going to equal that. So I've got cosine 53.13 equals my adjacent divided by 1,000. So I can just do 1,000 times cosine 53.13 equals 600. So what that gives me is that gives me this force coming in. I've got 800 there. I've got 600 here. I know this is 1,000. All right. What happens is I'm going to have to counteract that. So I know that this beam right here is going to have a force of 600, right? Because it's going to have to be pulling back from the force that this is applying. So if I look at my truss, what I knew is that this member is pushing towards that point. If it's pushing towards the point, what that means is that it is under compression. If it is pulling away from that point, that means that it is going to be under tension. So that is a good thing to know. So moving on, I'm going to move over to B because that's my next easiest. All right, and this was actually kind of simple. I know that 500 pounds is coming down, so I know that there must be 500 pounds pointing up. All right, it's pointing towards it, so I know it's compression. I've got 600 pounds going this way, so I know that I've got 600 pounds going that way. It's pointing away, so again, that means tension. So let's see here. We're probably going to look and solve for this one. That's the next easiest in my mind. So what we have is I've got 2,225 pounds of force going towards my joint. That means I'm going to have to come back with 2,225, thus letting me know that it's compression because it's pushing towards it. And there's really nothing counteracting that. So I know that's a 0, right? Because to solve it, it's going to have to work that way. So we have that, and we found most of our forces in our diagram right now. The only thing that's left is this little booger of a problem right here. So let's go after this. What's going on is we're looking at that joint A. All right. We have 1,300 pounds of force going upward, which is reactionary force. We've got our 2,225 going to the left, which is reactionary force. We've already figured out that this one right here is under tension because the arrow is going away from it, 600 pounds of force. And we know that this is 0. Well, we don't really care about the 0 because it's not doing anything. And if I combine these two, right, I should end up with about 1625. That allows me to look at this vector and just sort of figure out that it's got to have two resultant forces. One being 1625 and the other being 1,300, just 1,300, not 1,300C. And with that, I can now look at it as if it's a triangle. All right, because I've got to have a vector that has 1625 in this direction and 1,300 in that direction, so I can just use the Pythagorean theorem to solve for it. So if I do that, I get a squared plus b squared equals c squared. I go through, I solve all this, and I get my value being 2,081. So if we check at it, it looks like everything is correct. This is actually came out of the MD Solids program, so I know this is accurate, and that's how we solve it.